Okay, welcome back. Today we're going to talk about limits of functions. Let's first see what is the idea. Okay, limit is basically expecting a behavior from if we say a function, we're expecting a behavior from function. It's a guessing of what is going to happen at a specific location. For example, if you look at this function x squared minus 5, f of x equals x squared minus 5, and here's a graph of f of x equals x squared minus 5. If I ask you what is f of 3, you can tell me, okay, I replace 3 squared minus 5, that must be 4. So I know that the expectation of the x value, sorry, let's change this to 2, f of 2. I want to figure out what is f of 2. 2 squared minus 5, which is going to be negative 1. Okay, let me erase these numbers. Okay, so if I ask you what is the value of 2, you should say, okay, the value of 2 must be somewhere like negative 1. And this graph that I drew, it's not 2 here. I was trying to do 3, but I changed my mind at some point and I forgot to fix it for the graph. So let me fix this graph. So at 2, we have something like negative 1. Let's say this is 2, and here, y value negative 1. Okay. Actually, let me fix the graph so be sure that it looks like at 2 we have y value of negative 1. Okay, so now what if we didn't have the graph the f of x function and say, okay, what if I tell you that at 1 I have the y value of 4? So if I tell you this trend, if I tell you the x value of 1, if you pick, y value is negative 4. If you pick x value of 1.5, the y value becomes negative 2.75. If you pick 1.9, the y value gets to be 1.39. So what am I doing is basically I'm looking at the pattern that if I pick specific x values, like starting with 1, what do I get is this y value. The next point, I'll give me this y value, so on, next, and so on. So what do I expect is if I get as close as I want to the x value of 2, what do you expect from the y value? So if you look at this pattern, I started from 1. I'm going closer and closer toward the y value, the x value of 2. And I'm trying to estimate what would happen with the y values. If you look at the y values, it starts with negative 4, negative 2.7, negative 1.1, negative 1.0, negative 1.003, and so on. So I expect to get the y value to get closer and closer to negative 1. I'm not sure if it's negative 1 if I don't have the exact value of the function, but I can say, okay, this is what I'm expecting. So my guess would be the y value would be negative 1. So if I follow these points, what do I expect is at 2, I expect the y value of negative 1 because the y values here are getting closer and closer to negative 1. Look at the y values. So if I pick the x values to be getting closer and closer to 2, the y values are getting closer and closer to negative 1. What if I pick the x values from the other side? What if I start with 3 and go 2.5, 2.1, 2.01? What happens to y value? So the x value starts with 4, then it would be 1.25, then it would be something like negative 0.05, and so on. So this x value, if you start from 3, go closer to 2, what do you get from the y values? That you see that you will approaching closer and closer to negative 1. This is negative point. These numbers they put here, this is like, let's say negative 0.95, negative 0.995. So I expect the y value to get closer and closer to negative 1. So what I say, this is the way that I can say this, and I can say that the limit of the function f of x, this is a notation, so I'm going to define this notation. This means that the y values of the function are going to be expecting to be L if x is getting close to a. So the way that we write it is we say limit of f of x as x is approaching to a. That means if, for our example, if x is getting close to 2, what do we expect from that? We expect the y values to be something like negative 1. So I can write this here and say limit f of x as x is getting close to 2 is negative 1. So this is an expectation. This is like guessing. So we're guessing that the limit the limit of f of x as x approaches to, in this case, value of 2. So x gets close to value of 2. If we're getting close to value of 2, what happens to y values? If you move along the curve, you will see that the y values are getting closer and closer to -1. So the y values are going to be getting close to -1. So this is an expectation of what happens if you get close to the x value of 2. There is one thing that you should notice, that we never look at the exact value of the point. If I know f of 2, I don't really care about the limit. So sometimes you do not have the value of the function, or the value of the function does not match the point. But this limit does not mean that it is going to be exactly the same as, this doesn't mean that you're looking for the f of 2. This means that you're guessing what happens around 2. So you're given some information around 2, and you're guessing what will happen if you pick exactly 2. It's not that you know the value. If you know the value, that doesn't mean that you know the limit. Okay. So here are a couple of examples just to understand what I'm talking about. So here, let's look. If I say given this graphs, so let's call this graph number 1, number 2, and number 3. Okay, let's focus on graph number 1. And I'm going to follow the path and say, they ask you to figure out what is the limit of f of x as x approaches to 1. So I found out x value of 1, means move toward 1 on the graph. What do you expect the y value to be? So if you move along this curve, I expect that the y value ends up to be, if it starts with 1, 1.1, 1 point something, and it gets closer and closer to this y value, whatever this is. In this case, it's going to be square root of 2. If I move the other direction, if I start from something like 0 or -1 and get closer and closer again to 1, what do I expect? Is expecting to be square root of 2. This is what I'm expecting. So the answer to this limit, first limit, is square root of 2. If you look at the second graph, what do you see? They ask you to find the limit of g of x as x approaching to 1. I'm approaching to 1 for the x value. So the x value, I'm moving along the curve. X value is 1 here. This is the point that I'm looking at. I'm looking at x equal to 1. And say, okay, I'm moving along this curve. What do I'm expecting to get? I'm expecting to get square root of 2. I'm not looking at 1. I'm expecting to see if I move along this curve, what do I expect? It's like assuming that you do not have this information exactly at this point. Ignore this and say, okay, what do you expect? You expect to get square root of 2. What if I move from the other side? If I move toward the x value of 1, what do I expect? Again, I expect that y value to be square root of 2. Okay, so the limit in this case for the second example is again square root of 2. If you look at the third example, it's the same thing. You follow the path the curve goes and say, okay, what do I expect? If you move from the right side, I expect y value to be root 2. If I move along the x from the left side, I still expect the y value to be square root of 2. This is the expectation of what will happen. It doesn't mean that it definitely is going to be that number, but you're guessing that it's going to approach to this value. So now let's compare it to the value of the function exactly. So if you look at the first graph, if I ask you what is f of 1, I ask you what is the value of the function exactly at 1. You look at the 1, there is no limit. You look at the 1 and say, okay, this is the point on the graph, corresponding y value, square root of 2. How about if I look at the second function, and g of 1? At 1, what is the y value? This is an open circle, so that is not the y value. The y value is this point, square root of 3. And you see that even though the limit is telling you square root of 2, that doesn't mean that the value of the function is going to be that. That means we expect square root of 2, but something happened and the function has a jump, and there is square root of 3 for the y value. I don't really care if it's this. There is nothing wrong with these two. It doesn't mean that this is kind of discontinuous function. We'll discuss this, but it doesn't mean that you got something wrong. This means that you're expecting to get square root of 2. And if you look at the third graph and you say, okay, what is the h at 1? The function h at 1 means I look at 1. What is the y value? This is an open circle. There is no other point. So h of 1 is undefined. in this case. There's no point on the for x value of 1. There is no y value. That means 1 was not in the domain at all. So you can have the same value, you can have different values, or you can have undefined value for the function as well. This is possible for the limit as well. So what I'm gonna say is that your expectation is what I'm looking for as we're talking about the limit. If you approach to that point, what do you expect? You expect the y value to be root 2. Sometimes you might get disappointed and say, okay, it's not the same as the value of the function, but that doesn't mean that the limit was wrong. That means, okay, the function is discontinuous or something is wrong with the function. Okay, here's what we do. Okay, so sometimes they ask you to find the limit of sine x divided by x. This is not an easy function. If you look at this function, limit sine x divided by x, graphing it is not going to be that easy. But what you can do is, okay, you can start saying that I want to approach to x value of 0. X value in this case is 0. Let me focus on this. That means I'm going to create a table and guess what will happen. So this is the table that I created. Pick x values of 1, 0.1, 0.001, 0.0001, and so on. You try to approach the value of 0 for x, and you try to estimate what would happen for the y value. If you follow this and say, okay, if I replace 1 for x into the function, your function in this case is sine x divided by x. If I put the 1 in there, sine of 1 divided by 1 would be 0.84147 and so on. You can use a calculator. If you replace 0.1 for x, what do you get is 0.99. If you replace 0.01, you will get 0.999 and so on. What do you see is at the end, you're approaching to a specific y value. What is that y value? You can guess it is 1, 0.9999 and so on, so it would be 1. The same, if I approach to 0 you have two directions to approach 0. One is starting from 1 approaching to 0, and the other one is from -1 you approach to 0. You can start from -0.1. You don't need to start from that far away. You can start from -0.01. But you just follow the trend to see what will happen. And if you do that again, on the right side, what do you guess is the y values are if you see increasing toward specific value of 1. So if you look at these points, what do you see is if I draw these points, 1 and 0.8, so at 1 you have 0.8, at 0.01 you have 0.99, and you'll have next one 0.99 and so on. So what do you see is these points. You pick more points, this is the trend that you'll see. On both sides, you'll see something like that. If you put 0 exactly into the function, if I ask you what is f of 0, you cannot calculate it because you cannot divide by 0. This would be undefined. But we don't really care about the value of the function, as I mentioned earlier. I'm talking about the limit. I want to see what will happen, what would be my guess for this point. And you can see that our guess ended up to be at 1. I can say the limit of the function is supposed to be 1. At this point, we're guessing. We're not using any mathematical way of finding out what is the limit. We're just estimating what would happen. Later on, we will have some limit laws and we will use those. Okay, so at this point, you can always draw this table and pick a couple of points, approach to that y value to see what would you expect to get. It's not always nice. Sometimes the numbers are not going to follow a specific trend. Here, I have an example for you. If you look at the function sine 1 over x and say, okay, if they ask you what is the limit, sometimes they write limit f of x, sometimes they write limit sine 1 over x as x approaches to 0. These two have the same meaning since the function is already sine 1 over x. And they ask you what is this value. You create a table again and try to approach 0. Okay, so I picked 1.1, 0.01, 0.001. And if you look at the pattern, what you get is this point. It's at 1 and 0.8. Let's say this is 0.8. If you pick the 0.1, let's say this is 0.1. What do you get? Y value is 1.7. Sorry, 0.17. If you pick 0.01, what do you get for the y value is 0.98. If you pick 0.001, you get this point, which is negative 0.98. And what is the trend of this graph? The graph will go something like this. It's not going to be nice or something. It's going to look like this. Go up and come down again, over and over. It's going to follow this path. So what do you expect? At zero, what happens? You don't have a specific idea what's going to happen because there is too many isolation around zero. So what can I say is I cannot have any information. So in this case, I can say the limit does not exist because it doesn't approach to a specific value. It's just isolating between zero, between negative 1 and 1. So the graph would kind of look like this. It somehow approaches, then it starts isolating more and more, more and more. There is no way that you can see, okay, at zero, what happens exactly. It doesn't go through zero, maybe it goes up. So there is no way to guess what will happen around that point. So this is, at this point, we will say this limit does not exist because we cannot guess what will be the end result. There is no estimating. If you look at the trend, there is no specific trend. You do not approach to a specific value, just isolating around. The more point you pick, you will see that there is no specific trend. In the last example, you will see that the pattern will get closer and closer to 1. Okay, here's another example. If you look at this function f of x and I ask you what is f of 1/2 and not the limit, this means the value exactly at 1/2. What you do is you look at 1/2 and say, okay, there is this point as well as this point. This one is empty open circle, so the y value is specifically at 1/2 is going to be 1, going to be correspond to that. But if I ask you what is the limit of the function as x approaches to 1/2, then let's follow the graph. Okay, if I'm getting closer to 1/2, and let's follow it on the curve. Sorry, let's follow in the curve. If I'm approaching to 1/2 in this direction on the curve, what do you expect? Before you get to 1/2, what do you expect the y value to be? The y value turns out to be 1. If I follow the curve from the other side, before I get to x value of 1/2, this is 1/2 again. Before I reach to 1/2 for the x value, if I'm following this pattern, what do I expect is the y value? I expect the y value to be 2. Which one is the correct answer? We don't know. If you remember that the function cannot have 2 different y values, otherwise it wouldn't be a function. So this is the same idea. If your limit has 2 different values, right side is going to give you a different value than the left side. In this case, you cannot accept either. You say the limit does not exist. This is what I'm going to talk about as we go on. This is what we built on is one-sided limit. That means you have to focus on different side. Okay, so in last example, in this example, you can see that the limit on the right side, that means following the right curve, is not the same as the limit if you follow the left curve. They give you 2 different y values. You do not look at the specific point, you follow the curve to see what do you expect. You expect to get 1 if you follow the right curve. If you follow the left curve, you expect to get 2. So you say, okay, this 2 values, I do not know which one to pick, so the limit does not exist. One-sided limit, it only focuses on one side. As the name says, it says, okay, limit f of x as x approaches to a from left equals to L. There are 2 ways to read it. You say left-hand limit would be f of x at left-hand limit of f of x at x approaches to when x approaches to a specific value of a is going to be L, or you can say normally we use this second way, limit of f of x as x approaches to a constant a from the left side equals to L. This is normal, the common way. And left-hand side uses this negative sign notation. It's just a notation. You say it doesn't mean that number is negative. It means you're approaching to that number from the left side. If you look at the last example, I can say, okay, limit f of x as x approaches to 1/2 from left side. This negative sign doesn't mean that you pick negative 1/2. It means you're approaching 1/2, but you use the left curve. The approach through the left curve. What do you expect from the y value? the y value is approaching closer and closer to 2, I'll say this must be 2. The same, you can think about the limit from the right side. As x approaches to 1/2, positive sign above means from the right side. That doesn't mean positive 1/2. I'm approaching to 1/2 on the curve. You don't have to go miles away. You can start from here. I'm approaching to 1/2. But before I get to 1/2 using the right curve, I can guess that, okay, the y values turn out to be 1. These two are the left and right hand side limit for the function f. And it is clear that they do not equal to each other. This one is 1, the other one is 2. If that happens, then you say the function does not have a limit. That's one of the next things that I wanted to mention, is if the left-hand side, if the limit on the left-hand side and the right-hand side are equal, then that's going to be exactly the limit of the function. If we look at the function and say, okay, the limit on the right-hand side is not the same as the limit on the left-hand side, then you say the function does not have a limit at its specific point. This is what we talked about. At 1/2, there was no limit. But if they do match up, if they were both equal to 2, that means if you follow the left curve and the right curve, then they're both going to be 2. That means the limit of the function, as x approaches to 1/2, would be exactly 2, because these two equal to each other. That means both curves ends up to be the same expectation. In this example for us, they're not exactly the same, so I can say simply this is undefined, or sorry, does not exist. DNA. Okay, so this theorem is basically saying that if the left-hand side and right-hand side limit are equal, then the limit is going to be exactly the same as that. If the limits are left and right are not equal, then the total limit without any left or right notation, that doesn't exist. So here's an example just to go through that. If you look at this curve, this color to green, and say, okay, let's try to figure out limit f of x as x approaches to 2 from left as well as from right, as well as without any specific direction. Let's calculate each one. Limit f of x as x approaches to 2 from left side. Sorry, 1. Why did I pick 2? I don't know why did I pick 2. 1. Okay, let's approach 1 from left and right. Okay, so from left, so I'm approaching 1 from left. Follow the curve on the left side. This is the curve on the left side. What do I expect from the y value? The y value is getting closer and closer to 2. So y expectation is 2. Approaching to 1 from right hand side, and start on the curve, move toward that. What is the y value? The y value is approaching 1. So what is the total limit? Again, the left and right, if they do not match, I can simply say this doesn't exist. That means if you follow two curves, they do not going to match up to each other. There is no specific limit at that specific point, unless you're given a direction. If they say right hand side, there is a limit. If they say left hand side, there is another limit. If you look at the limit of the function at 4, for example, from right as well as from left, as well as without any sign, and let's figure that out. Approaching 4 from right side is approaching 4 from right side. I'm following this curve. What do I expect? I expect a y value of 3. Approaching 4 from left side, do not start from here and say, okay, I'm going to approach 2. You have to stop at 4. I'm going to get closer and closer to the x value of 4. You don't need to be at this point. You have to get close to it, but you can expect that the y value is going to be at 3. What is the total limit? I don't need to look at the function anymore. I can see, okay, the left and right, they're both 3, so the limit must be 3. If I ask you, what is f of 4? Now you look at the exact value of 4 and say, okay, f of 4, it's an open circle, so it's undefined. If I ask you what is f of 2, f of 1, sorry, at 1, I look at the value of 1. Here's a closed point at 1. The other one is open circle. So at 1, y value is 1. Okay, there is a difference between the value, exact point, and the limit. The limit is what you expect. The value is what you look at exactly at that specific x point. Okay, one more thing, the infinite limits. Infinite limits means sometimes when you're approaching to a specific value, the function is just increasing or totally decreasing. The infinite limit means sometimes I'm approaching an x value and the y value are just going toward positive infinity or negative infinity. Let's say if they approach positive infinity, say, okay, limit of f of x as x approaches to specific value of a is infinity or negative infinity. I used green, or doesn't mean they both happen at the same time. If you look at the curve, the red curve, graph number 1, y equal to f of x. If I'm approaching a, what happens to the value of the function? If I approach a from left and right side, what happens? The curve is just increasing, going up. The y values are continuously increasing. So at a, the y value is going to be positive infinity. So this limit f of x as x approaches to a is going to be positive infinity. On the other side, if you look at the second curve, if you look at the green curve, you see what the y values happen. What happens to the y value when x approaches to a? They're getting larger, but in the negative direction. So they're going smaller and smaller in the terms of value, decreasing. It's a large number, but it's negative, so it's negative infinity. It doesn't stop, it's continuously going on. This point A that I use dashed line for it, this is what we call a vertical asymptote. Vertical asymptote is where the function around that point, around that x value, are increasing toward positive infinity or negative infinity. Sometimes the curves are not in the same direction. For example, instead of being like that, sometimes it's like this. And now still a is a vertical asymptote, but now the limit, it doesn't exist, because on one side, what you see is on the right side, you see positive infinity. But if I look at the limit following the left curve, if I follow the left curve, what do I get is I'm going toward negative infinity. These two infinities do not match. So the limit of the function, the limit of f of x as x approaches to a, if we get close to a, what do I have? I have positive infinity and negative infinity. They do not match, so I can say the limit does not exist. These two do not converge to a specific value. They go different direction. But for our case, originally it was these two curve matching up. So that's why we had positive infinity. They both go toward positive infinity. Okay, let me keep this the other way so you have the notation. So definition, here's an important definition for the vertical asymptote. We say x equal to a is a vertical asymptote. Again, that dashed line. That dashed line is a vertical line. We say x equal to a, x at that point, is a vertical asymptote if one of the following happens. One of the limits, either right side, left side, or both, approach to either positive infinity or negative infinity. So we want to have at least a form of something like this curve on the right side approaches to infinity. Or maybe we don't have that, maybe we have only this one. That is good enough to say x equal to a is a vertical asymptote. Or maybe the other way. Maybe both going this way. Right? So as long as you have one of these curves increasing or totally decreasing at around specific value of a, then you say x equal to a is a vertical asymptote. Okay, this is very useful for the definition to find vertical asymptotes. Let me draw this. You do not need to have both sides. Just one side is good enough. You can have this curve. Nothing wrong with this. A is still considered a vertical asymptote because the function is around a at the right hand side is going to be increasing towards infinity. The limit at a does not exist because the left and right limit are not the same thing, but you can have A as a vertical asymptote. Okay, normally this happens for rational functions. So it's important that you know where the vertical asymptote is. Later on, we will discuss how to find that specifically. Okay, so given f of x equals tangent x, if you know how to graph the tangent x, then you can figure out where the vertical asymptote is. Vertical asymptote for this case, review the sine, cosine, and tangent functions, just tangent and cotangent, just to know that there is specific points that they have vertical asymptotes. You can always figure them out by writing in terms of rational functions. So in this case, tangent function, this is how the tangent function looks like. If you look at pi half, for example, what do you see the limit around pi half? The limit of the function tangent x as x approaches to pi half. On the right side, if I'm approaching to pi half from the right side, I'm following the curve on the right side. What do I expect? I expect negative infinity. The moment that happens, I do not need to look at the other side. I can say x equal to pi half is the vertical asymptote. Okay, but if I'm looking for the total limit doesn't exist because the right-hand side is not the same as the left-hand side. But that doesn't affect the fact that x equal to pi half is a vertical asymptote. The same, negative pi half would be a vertical asymptote, 3 pi half would be a vertical asymptote. If you continue to redraw this graph, because the tangent keep repeating itself, so then you will get negative 3 pi half, negative 5 pi half, and so on. All those would be vertical asymptotes. Okay, so vertical asymptotes normally happens when you deal with the infinite limit around x equal to the point where you have an infinite limit. At this point, I'm going to stop here. Most of our focus was either you create a table or you use a graph to find the limit of the function. Later on in the next section, we're going to discuss how to find the limit if you do not have the graph by just calculating for using specific laws of limit. Okay, let me stop here.